Okay, so how many motors do you think are in this classroom? Any guesses? Okay, any number? And if you answer any number, you get a point awarded for today. Anybody?
30.
30. It's up to you if you want to raise your hands, otherwise you can just throw the answer. Yeah.
45.
45.
10.
Anybody else?
1,000.
1,000. Fantastic. Okay, let me complete the whole range. Right, so those of you who said those numbers, can you tell me where the motors are? And if you can, if you know, tell me what kind of motors they are. Others are also welcome to chime in. Yep.
We have the motors here on the table. All of our laptops are going to have some DC motors. I'm sure that, well, that looks like a non-electronic projector screen, but.
On table, our laptops are going to have motors where?
What's that?
Laptops are going to have motor for what?
Cooling.
Cooling. While we're on the topic of laptops, any other motors in the laptop? Yep.
Well, not in the laptop, but the HVAC system.
HVAC. Anybody wants to take a guess as to what this what type of motor is in the laptop?
DC.
DC, yep, in the back.
Brushed.
Brush, perfect. We'll get to what this is, brushless DC motor. It's somewhat of a misnomer. I'll get to that in a minute. All right. Anybody wants to guess what a HVAC motor is going to be? So HVAC, for those who are heating, ventilation, and air conditioning. So this typically might be an induction motor or a permanent magnet synchronous motor. So IM is induction motor, PMSM is permanent magnet synchronous motor. Sometimes I'll also write PMAC, which is basically permanent magnet AC motor. Those terms are just interchangeably used, right? Okay, where else are there motors? Anybody who wants to complete the other motor in the laptop? Are there any other motors in the laptop? All right, okay, we'll get to that then. Yep. You had an answer.
Clock.
Clock. Anybody wants to get what the motor is in the clock? What type of motor? Yep.
I think some of them are AC because they're like synchronized with the line frequency.
It could be AC, but not sure if the one on the wall there is an AC motor. Yep.
Could be a stepper motor.
Stepper motor. So it could be either one of those. If it so those some of those the battery operated, those are definitely going to be stepper motor. For the clock in my office that I have, all the faculty's office, it's connected to the wall plug. Those would likely be an AC motor driven from the 60 Hz frequency that we have. Right? Any other motors?
I think maybe depending on your phone, some have little motors for the vibration.
All right. Phone. Haptic feedback. Any want to guess what kind of motor it is? All right, we'll get to it. Any other motors? Yep.
Are the speakers considered motors?
Speaker, we will. So since we are in a motor course, everything that moves, we'll claim it as a motor. Whether it's a motor or not, we will claim it. Yep, in the back.
In the sprinklers.
The sprinklers, I'm sorry, I'm not sure. I don't think so. But the problem with putting a motor in the sprinkler is during emergency, if the electricity goes out, you would still want the sprinkler system to operate, right? So it might not be, it might be just hydraulic system. I don't think it'll be a motor there, but I might be wrong. I'll check and confirm once I know it for sure. I'll put it on. Right? Yep.
A fire alarm?
Fire alarm. Again, that I would just classify it under the speaker part of it. Anybody else? Yep.
The projector probably has a cooling fan, maybe to change the focus of it, like the stepper motor.
Fantastic. Projector. Two things. Cooling fan. And focus on the lens. Anybody who wants to give an answer as to where a phone and a laptop might have additional? Yep.
Is there like a coil in the
camera to adjust the focus?
Perfect. So same focus. A different kind of motor, we'll get to it, but phone, camera, focus, lens, you have motor, and since speaker was already given, we have the speaker as well here. Right, any other motors?
For people who wear watches,
Watches, perfect. Again, same haptic feedback. As well as you have your speaker. Any other?
Air purifiers?
What was it?
Air purifiers?
Air purifier, perfect. Will be a DC motor. Anything else? Was it? Camera. Think. However, there's one more that I could think of. So the camera, basically, they have this rotational aspect that tracks my motion. It doesn't track my motion, I have to manually do it, but it's rotatable. So this has a servo motor. Servo motor is just a fancy name for either a brushless DC motor or a permanent magnet synchronous motor or a DC motor with a control algorithm such that its angle can be controlled. Right. So basically the experiment that you'll be doing in the lab is a servo motor, making this DC motor behave like a servo motor so that you can control the exact angle that it goes to. So that's all the term servo motor means. It's just any of these three motors that angle can be controlled to a particular value. Okay, there's one more. Maybe wants to
Door locks.
door locks. So all of these doors are accessible, or at least not the front one, but I think the side one there. Wheelchair accessible doors. So those typically have a PMAC motor. And the reason they have a PMAC motor is there's basically a motor and a battery that's there. It's somewhat disconnected from the outlet. So every time you open the door, you push energy into it. So people who don't use the button on the wall and just push the door, you charge it by basically making this motor. So there is no difference between a motor and a generator. Right? If I apply electrical power into this and the shaft starts rotating, it operates as a motor. But when I rotate this by hand or by some other energy source, I can take energy out from the electrical system. So I convert mechanical to electrical or electrical to mechanical. So depending on which way the power flows, the same thing as a motor compared to a generator. So every time you push the door, you charge up the battery because this motor is operating as a generator. And when somebody needs to push the button to open the door, it takes the energy out of the battery and makes it operate as a motor. All right, I think that covers all the things. And if you count, every one of us has typically a phone in our pocket. So each phone has about 3 motors in there. And we have about 38 students. So that far exceeds the 45, right? And then you have your laptops. In the laptop, there are other as well. If you have old laptops, you have a hard disk, right? Those again have motors. These are called spindle motors. It is just a marketing name because they look like a motor, but these typically have a BLDC motor, an outer runner, outer rotor BLDC motor. So what I mean by outer rotor is typically for these motors that you see on the lab table, the rotor is on the inside and the stator is on the outside. How many of you have seen like a quadcopter motor? Okay, those are typically the rotor is on the outside. And there are reasons to do that because when you put the rotor on the outside, it can be much more flatter, right? You can have this tiny pancake structure instead of having this elongated length because the air gap is pretty large. So you can produce more torque. We'll get to all of those theory later, but even with a smaller magnet length, you can get more torque out of the motor. So that's one advantage. And the other advantage is like when these rotors rotate, I'll show a structure of this rotor later, but basically magnets are stuck onto the rotor using glue. If it rotates too fast, the magnet can just come off of the rotor, right? But if it's an outer rotor and the magnets are stuck to the inside wall of the rotor, if it rotates faster and faster, centrifugal force will just push it onto the rotor, which is rotating, right? So it won't come out of the rotor. So that's why higher speed rotating rotors might end up being outer rotor, while slower rotating rotors would end up being inner rotor typically. So that's all the differences between an outer rotor and inner rotor, but they all operate the same. So BLDC versus PMAC. In this course, we'll only look at PMS and PMAC same. We'll look at this, we won't look at this. So there's somewhat of a misnomer here. BLDC is actually an AC motor. It is just an AC motor which has a drive associated with it. So the drive would take a DC voltage, and then the power, by drive, I mean a power electronic converter, it will convert the DC voltage into AC voltage, right? And then drive this motor. So it's usually a motor and some kind of power electronic device is connected together. And there is another confusion in the term when we use BLDC. It comes from the fact that if I take this motor and I rotate this at a constant speed, so we do this in the lab where we attach this rotor to a drilling machine head and just rotate the drilling machine so that it rotates at a constant speed. And we can connect these two prongs to the oscilloscope. So when you come to the lab, you could try it too. And you'll see that the voltage looks like a perfect sine wave. Every time this rotor rotates a rotation, you'll get one sine wave coming out of it, assuming it's a simple two-pole machine. In case of a BLDC motor, it is supposed to, instead of looking like a sine, it's supposed to look like a trapezoidal back EMF. All right. But again, this term has been so kind of interchangeably used. Sometimes even machines with sinusoidal back EMF are sometimes referred to as BLDC. There is no strict theoretical definition as to what's BLDC, what is not. But for our consideration, the theory of operation is very similar to PMAC motor, so we won't worry too much about it, right? So those are all the motors. So these ones in the phone, these haptic feedback, they could come under two categories. They could be linear actuator. So these are basically just a bunch of coil onto which there is like a metal shaft with some kind of magnet or something. So in many cases, magnet won't be there. And there is a spring attached to this shaft so that that's keeping it in a position where it's outwards. When this coil is excited, the shaft gets pulled inside, right? And then when the coil is de-energized, again, it goes out. That's basically how you get that haptic feedback. And this is what used to be the older model of iPhones. I think even the later Samsung phones have this. The newer model of iPhones after I think iPhone 12 or something, they changed this haptic feedback to basically a bunch of coil. And there is a metal plate underneath this coil with two spring sides attached on one another. And this coil basically excites that metal plate and then it starts to oscillate back and forth, right? And the advantage of this is far more efficient and far more compact. But the operational principle is all pretty much the same in both the cases. Voice coil motor again operates in the same phenomenon kind of principle. You have a coil, you have a magnet, and there is a diaphragm attached to this coil, basically a plastic plate. And when current goes into this coil, you can either make it attract towards this magnet, depending on the direction of the current. We'll take a look at the theory later, or you can make it repel. And if you do that fast enough, you can basically start to hear sound, because sound is just compression of sound waves, right? Air molecules. So you can get that basically by just exciting this coil at whatever frequency you want it to be. So all of these three pretty much lie under the similar technology. It's just the way it's designed and applied is different. For instance, a voice coil would have a very large frequency operational range, while a haptic feedback would have a very tiny operating frequency range because it just vibrates at one particular frequency, not at all possible ranges of frequency, right? So all of these more things, whether you want to call it an actuator or a motor, that's totally up to you. Motors are not just things that rotate. There are things called linear motors as well, right? A maglev is kind of a motor because basically a motor that's, so if you take this three-phase motor, cut it open and lay it flat, that's what effectively a maglev train is, right? It's a linear motor of some sort. So again, these focus on the lens. All of those typically end up being one of these actuators. And then watch as haptic feedback, all of those fall under the same category. So for our case, we look at induction motor, permanent magnet synchronous motor, or PMAC, all both the same. These two fall under the category of AC motors, right? And then the DC motor itself, which could be a part of the servo motor, that is also what we will take a look at. So the final aspect is where was HVAC. So HVAC could either be an induction motor or permanent magnet synchronous motor. So on the table here, I have three motors. So this is a DC motor and this is a permanent magnet synchronous motor. Both of it have the same power rating, right? So that's the advantage of going with a permanent magnet AC motor, because in a DC motor, one of the biggest problem, as we will see later through this code, is almost a quarter of this motor is occupied by a mechanical structure called commutator, right? And this is very inefficient. It breaks down quite often, and it's also it causes huge amount of losses. So this is something that needs to be gotten rid of. So that was the reason why AC motors are typically used in high efficiency application, right? And they can end up being much, much smaller in size compared to a DC motor. But they also end up being a little bit more expensive because it's more complicated winding process. Because instead of just the one set of phase windings that are in a DC motor, you have three set of phase winding that needs to be wound by a machine, and then somebody has to assemble it. So on the table again here, I have an induction motor. So these both qualify under the AC motor. So these are all three-phase AC motors. As you can see, there are three-phase coils coming out. This one is just to get the speed and core feedback. So ignore that for now. And in the PMAC motor that I have on the left is almost 3 times the power rating of the induction motor that I have. Right? All right. But if you can take a look at the induction motor, it's almost twice the volume of the PMAC motor that I have. So compared to a PMAC motor, induction motor is typically 2 to 7 times larger in volume if you have both same power rating of both the motors. So what the advantage of the induction motor is, in case of permanent magnet synchronous motor, you have magnets on the rotor. Induction motor has no magnets at all. And what is the biggest problem with magnets? Expensive. Any other problems? They end up being quite brittle. And one of the most serious problems that we are facing right now is typically these magnets are neodymium magnet, and China is the only single source country that's having these resources. Right? So if there were some problems that involve China and the US, China could put a sanction and we will have no access to neodymium magnet. So that's a very big problem. So many companies are trying to find out ways of avoiding this magnet or using a different kind of material for magnets and so on and so forth. So induction motor doesn't use any magnets at all, but it also makes it very bulky and big. But it makes it extremely rigid. So when you have like oil or drilling plays or something, they would typically use induction motor because they are far more robust. A permanent magnet synchronous motor, the magnets could crack or some damage could occur, or magnets could get demagnetized. There are a whole bunch of problems that could occur with it. Now, when you look at EVs, where space is very constrained and efficiency is the primary motivational factor there because battery charge is very important, we usually stick with the permanent magnet synchronous motor, but the cost overhead is okay compared to what we gain an advantage of it. So when we go to HVAC, it depends on what the spacing on your rooftop is. If you have sufficiently large spacing and the rooftop can take a heavy load, then you would go with the induction motor because it's far more bigger in volume and weight. But if you're limited in space and you want to operate it very efficiently, your HVAC would typically be a PMAC, and that, with that, it will also be more expensive. Right? Anybody have any questions so far? Okay. With that, let's me go to the next question. So, who do you think invented the first motor? And what was the first motor? Again, there are no wrong answers. Yep.
Did Faraday make a solenoid or
What was it?
Faraday, Michael Faraday?
Faraday. Okay. What motor? Was it a DC motor, AC motor?
I'm not sure.
Okay. Do you know which year?
No.
Okay. Around 1820s. Anyone else? There are no wrong answers. Any guess is okay. There has to be more guesses than just Faraday.
Tesla did the first AC motor in, I think it was 1890s.
1890s. That's a perfect year. Do you know which country he's from? Croatia, modern day Croatia. Back then it was part of the Austrian Empire. Any other guesses? Typically, whenever someone says Tesla, there's always another answer for another. There are no wrong answers. Yeah.
Thomas Edison.
Thomas Edison. Do you know which type of motor he invented? Tesla, do you know which type of motor? AC, PMAC or induction?
I'm gonna guess induction.
Okay. So Edison, around the same time period, 1870s to 19. And we want to guess which country he's from?
United States.
USA. Michael Faraday? What is? He's British. Okay, so Edison was a big proponent of DC, but he did not invent DC motor. He was a big proponent of the DC energy system, while Tesla was a proponent of the AC energy system. But he tried to push DC power as much as possible. That didn't work out though, for quite a good reasons we'll see later in this course. Do you know what this time period is called in US history? 1870 to 1890s?
Industrial Revolution.
Industrial Revolution? Not yet. Very good answer though. So there's a show on HBO called Gilded Age. This period was called the Gilded Age, where there was enormous wealth disparity. We had the Astors, we had JP Morgan, Carnegie Mellon, all of these people were Andrew Mellon, Carnegie's, all of them were during this time period. There was a particular name for those group of people. Maybe you know. They were called robber barons because they would basically have monopolies and form groups and discuss the terms and then do whatever they wanted. Right before this was the Reconstruction era, and right after this was the Progressive era. What happened during the Progressive era? This is all not on the exam, it's just keeping the course like, yep.
There are antitrust cases.
Okay. Do you know who was the president? Yep.
Was it Roosevelt?
Perfect. Teddy Roosevelt. Oh, this was first term. So you basically use the Sherman Act, which was passed much before Teddy Roosevelt to break up these big monopolies that existed. Right. So breaking up monopolies is not something new, but it was extremely bad in this period, and it got started to break up. So Edison was trying to push through DC, but that never worked out. Nikola Tesla was on the AC side. That didn't end up work out. But as we'll see, Tesla is usually identified as the guy who invented AC motor, but he is not the one who invented the AC motor first, and he's definitely not the structure that he has is not the structure of the motor that we use nowadays, right? So it's somewhat of misattribution. It's very common in the history. So Michael Faraday did invent the first electromagnetic motor. So the structure was extremely simple. So he had a chalice filled with mercury, and there was this rod, metal rod, onto which there was a hook, copper rod. So this copper rod was hooked onto it so that it can rotate freely. Okay? And then at the stem of the chalice, there was a magnet. Polarity of the magnet doesn't matter. And then the base was again a copper, some kind of conductor plate. Copper plate here, copper plate here. In between these two copper plates were insulated by wood. Right? So he applied negative charge to the bottom plate. Again, the polarity doesn't matter. It can be positive on the bottom plate, negative on the top plate. And then the opposite charge on the top plate. So what he observed is that current starts to flow through this conductor, and the reason he used mercury is because it's electrically conductive, and this chalice itself was a copper or a silver, unsure what it is, chalice. So current can flow through this rod, through the mercury, and complete the contact through the chalice and back to the negative terminal. So what he observed is once current started flowing in the presence of a magnet, he saw that the rod started to rotate. Right? So that's the very primitive DC motor that we have on the table right here. And the purpose of this mercury is, in addition to being a conductive pathway, so why didn't he directly connect this rod to the cup? What would have happened? What was the purpose of the mercury there?
To allow for rotation.
It would not rotate basically. So if it was directly connected to this, it's going to start to get twisted, right? He needed some kind of mechanism that would have electrical contact, but mechanical isolation. What is the opposite of it? Where we have mechanical contact, but electrical isolation. What device does that? You all would have learned it in your first year circuit course.
Transformers.
Transformer. So this is basically a complementary pair of a transformer in some sort. So this was the initial version of what's called a commutator, liquid commutator. So what a commutator does, so that's the section of this motor, the back quarter of it is basically a commutator that's being involved there. It doesn't, of course, have mercury. It has some kind of copper rings with graphite brushes to make electrical contact while giving rotational isolation, right? So that was the purpose of mercury. So what you observe is the rod starts to rotate. And so this is the structure that we are going to develop further into a DC motor. So before we do that, why don't we no longer use mercury as the commutator? What's the problem with mercury? Is there any problem with mercury? Poisonous, right? So elemental mercury in itself is not poisonous. You can in fact play with your hands. Nothing is going to happen to you. Even if you inject like tiny amounts of mercury, your GI tract does not absorb mercury well. So it just pass through your system. But if you have vapor form of mercury, which is not easy, like you need to heat it up to get it into vapor state. And then you inhale it, it can, mess up with the signals in your central nervous system. So that's the problem with mercury. But the bigger problem with mercury is when it gets into the water system, right, it can get converted to what's called methyl mercury, Cl minus or something, by sulfate reducing bacteria. And this methyl mercury is extremely poisonous. It can get easily absorbed by either ingestion or even through contact through multiple mechanisms. So that's why, so these are then consumed by phytoplanktons and then diatoms and then all those other species of the chain, and they start to accumulate in the food chain. Right? These mercury in itself is not absorbent, but methyl mercury is liposoluble. So what it means is when fishes consume them, they get stored in the fat of the fish. And then when you consume the fish, it gets stored in your own body, and it can cause kidney failure, and it can cause central nervous system damage. And it's even more damaging to fetuses. So that's why pregnant women are typically recommended not to eat fish at all, because even a tiny amount can directly go past the placental wall and then interact with the developing fetus and cause permanent neurological damages. So that is the reason we don't go with mercury, because it's very toxic once it enters the atmosphere and gets converted to methyl mercury. The biggest source of mercury itself in our day-to-day life is basically coal. When you burn coal, it's a byproduct from the oil industry. It's a byproduct, and naturally it occurs in volcano. There's nothing we can do about it, but at least coal we can phase it out so that this mercury poisoning doesn't keep happening. Okay, so this was the earlier structure of DC motors that Faraday had created. But before this came about, there was a whole bunch of work that was done in the same time period, 1810 to 1825, by Ørsted and Ampere, and of course Faraday. Anybody want to guess which country Ørsted is from? He was a Danish. And then Ampere. That's a very easy guess. From the name you can guess.
French.
French. Faraday, of course. The reason I give the nationality of each of these people is it's not a single person from a single country that came up with a great invention. All right? It's a worldwide effort contributing incremental changes, which ended up being an extremely large achievement. Okay. So what did Ørsted figure out as related to this particular invention? What was Ørsted's contribution in electromagnetic theory? He had a lot of other contributions, but in this particular area, what did he do? Some of you might have heard these stories about Ørsted in your high school AP physics or something. So there's this story that when he was walking by with a compass in his pocket near a current carrying conductor, the compass deflected, and he figured out there is some kind of relationship between electricity and magnetism. Right? That's purely a mythology. That is not how it happened. He in fact spent decades before that studying the link between magnetism and electricity. It was a big problem of the time period, early part of the 19th century. And numerous people were working on it, and Ørsted was one of the lead people who had worked on it. So he establishes basically the relationship between current and magnetic field. Anybody know what Ampere did? What was his contribution? There are no wrong guesses. So whenever we talk about all of these voice, coil, all of those, these are in some sense a solenoid. Right? Every time we use a solenoid, we have Ampere to thank for. Basically had a coil, he passed current, and he figured that this created a magnetic field similar to as if a magnet was present there. Right? So current carrying coil has the same effect as this magnet had in Faraday's experiment. And the other important contribution he did is if you take this coil and put an iron block within it, the magnetic field generated by this is far more powerful, orders of magnitude powerful compared to just air gap alone. Okay? So we'll get to both of this in our Maxwell's theory equation lecture, but that was his contributing factor where a current carrying conductor produces a magnetic field very similar to what you can do with a magnet. So basically what Faraday did here is we all know as kids we have played with magnet, I still do. When you have two magnets, right, they attract or repel. So all he did was by passing a current carrying conductor, Ampere already established that a current carrying conductor behaves just like a magnet. Okay? Faraday himself, anybody remember? Again from electromagnetic theory, what did he demonstrate? Of course, that experiment is there. Otherwise, yeah.
Well, the voltage creates a changing magnetic flux.
Okay, so if you take a magnet and move this magnet around, you will start to measure voltage. So changing magnetic field ends up creating a voltage. Or the other way of saying it is changing voltage would end up creating a varying magnetic field on the other end. So there was another thing he did as well, which was a precursor to that experiment right there. So he took two conductors, current carrying conductors, and he passed current in both of them. Do you think these conductors would attract or they would repel? There are only two options. And there are no wrong answers. So go ahead.
Correct.
Attract. Anybody else?
Repel.
Repel. So somewhat counterintuitive. It does attract. From electrostatic, we might think two light charges would repel, so light currents would also repel. That's not how that works. Do you know what law dictates this?
Faraday's law.
What was that?
Faraday's law.
Not Faraday's law. What was it?
The right hand rule.
Right hand rule. All right. So that's a rule.
Yeah, I know it's not a law.
All right. But that was a good guess. So there is a much more fundamental. So the rule. So you can use multiple different ways. Some people use the left hand thumb rule. Some people use the right hand thumb rule. I myself go with the right hand thumb rule where you curl your hand around. So if the current is in this direction, this one is going to create magnetic fields around the current carrying conductor, same as what your right hand curling around it in this particular direction. And the other one is going to create its own magnetic field in the same way. So the magnetic field from this conductor is going to intersect with this current carrying conductor. So let me use different colors here. So this is the second current carrying conductor. This is the first current carrying conductor. This is going to end up setting up magnetic fields that are going to interact with this in this direction. So if I just draw the vector alone, so this is the current, and this is our magnetic field B due to second conductor. This is current due to the first conductor. Right? So the magnetic field of the second conductor is going to interact with the current of the first conductor to create a force such that if you take your right hand and curl around, starting from the first vector to the second vector, whichever direction your thumb points is the direction of the force. So the thumb would point this direction. So the second conductor would be attracted like this, and of course from Newton's law, equal and opposite forces. So the other one would be attracted towards that one, right? You can do the same thing for that current as well. So current comes out like this. Magnetic field is in the other way. So this magnetic field would interact in the other direction. So you will still get the same force. Or you could use the left hand thumb rule, the left hand rule as well, which I'm not too familiar with. Okay. So that is the law, but equation, there is a rule, the equation that governs this though is the Lorentz force equation, which again we'll go into significant detail later. But let me just jot down the equation here. So if we ignore the electric field, which we are allowed to ignore in this particular case, because when the current is flowing, there's an equal amount of positive and negative charge. There is no charge disparity. There is no capacitance here. Okay? So there is no electrostatic field that's established on a macroscopic level. It's purely the current carrying conductor establishing a magnetic field. So the second section of it can be ignored. We'll do a much more rigorous analysis later, but for now this can be ignored. So all we have is this first part alone. So this again we'll derive later in class, can be rewritten as I times L cross B. Both of these are one and the same. So this is what basically says if we have a current carrying conductor, it experiences in a magnetic field is going to experience a force given by I times L cross B. As simple as that. There's an easier way to remember this bill, right? But there's a problem with remembering it as bill. Just remember it's a cross bill. So once you have bill, you need to swap the direction of I and B. Right? Because in cross product, the order is important. I cross B is not the same as B cross I. The direction would be opposite in this case. So it's just bill reversed around. And whether you want to put the length as the vector or a current as the vector, that's totally up to you. My personal preference is having the current be a vector and the length be a scalar quantity. But a lot of people have trouble thinking of current as a vector. A lot of textbooks still use length as the vector. So that's totally up to you how you want to see it, because people are comfortable with current density being a vector but not current for whatever unknown reason. Okay, so this is the formula that will basically tell us what the force is going to be. Okay, so this was not the first motor though, electric motor. There were electric motors before this. So the first electric motor was invented by a guy called Andrew Gordon. In 1740s, the exact year is unknown, lost to history. He was a Scottish monk. Right? So he came up with this ingenious apparatus. Basically, a pinwheel with extremely sharp needle-like tips. These are all made out of copper or aluminum, some kind of conductive material, mounted on some kind of tower, which is again conductor. And what he did is he applied a very high charge potential to this tower. Once he applies a charge, where do you think these charges are going to accumulate? In the tower structure, which point do you think the charges would end up accumulating?
Like on the edges.
On the edges. Okay. On the very tip where it's extremely sharp, that is where the charges start to concentrate. Anybody want to tell me why that happens? We all know that intuitively, right? Charges accumulate at the tip because we all would have done, yeah.
Is it because everything needs to be the same voltage?
Everything has to be equipotential, perfect. So we know this somewhat intuitively. When we were kids, we probably rub our winter socks on carpet and go and touch our friends with our tip of a finger to give them electrostatic shock. We don't do it with the palm because that is not where the charges accumulate. It's always at the tips where the charges accumulate. We know that intuitively, but mathematically, it's basically, let's say you have a sphere with a lot of charges on it, right? And let's say this is being powered by some Van de Graaff generator or something that's maintaining it at 100 volts potential. If I take a wire and connect another sphere, okay, charges are going to move from here, from the generator to the sphere to the other sphere, so that the whole system is now equipotential. And this happens in metals. Of course, this has to be a metallic sphere. And this happens in metals because there are a lot of free charge on metal surface. If there is a difference in this voltage, right, there is going to be an electric field that's going to be created because What's the relationship between voltage and electric field? What's the units of electric field?
Volts per meter.
Volts per meter. What is the relationship between voltage and electric field? You can guess it from the units.
E dot dr,
Hold it.
like E equals E dot dr.
P equals E dot dr, right? So if you have two parallel plate capacitor and there is some voltage between it, 0 volts, 100 volts, and the potential difference is 100, the electric field is just going to be 100 divided by whatever this distance is. Let's say this is 1 meter because too large. Right? So that's just 100 volts per meter. There's going to be our electric field between the two plates. And this is positive, this is negative. Right? So that's pretty much it. So if you have a one-dimensional case, it's pretty straightforward. Electric field is dV by dl, differential change in the voltage divided by the differential change in the length. And this is only applicable. How many of you have done the electromagnetic theory course? All right. When is this formula applicable? When can an electric field be represented as a function of the scalar vector field? There's a big caveat as to when you can do that. It's not always true.
Conservative field.
When is it conservative? That's a very good answer. The field is not always conservative.
When it's like closed, like a closed loop system.
If that's the definition of conservative field. So if you have an electric field and you do a closed loop, you wouldn't have done any work. But if you had a magnetic field and you did the same loop, you would have done work on it. Right? Magnetic field is not a conservative field. It's a property of the electric field. So this is only applicable in case of electrostatic field. All right, when you have magnetic wave field as well varying magnetic field, E is not purely a function of the scalar vector field alone. There is a vector potential that's defined as A or something like that, right? Which is completely different. So we can only talk about this relationship in electrostatic field, and that's somewhat important as to why in case of a motor, the voltage that's coming out of the terminal is called back EMF, and we don't call that typically as a voltage. So it goes back to this part. We'll get to that later though. Right? So this is in case of one-dimensional case. In case of three-dimensional case, you just use this divergence expression. We'll get to what divergence is in more detail, but it's basically differentiating along each axis and giving a vector nomenclature to the resulting electric field. All right, so this is what is going to be our electric field. So this potential is too different. If this potential is different from this potential, because of this separation in distance, there's going to be an electric field. When there is an electric field, the charge is going to experience a force. And that force is going to be such that it's going to reintroduce the charge from lower potential, higher potential to lower potential, assuming the charge to be positive. So the charge would move from 100 volts to 0 volts so that these two end up equating to be the same potential at the end of the day. So then why in the hell would charges accumulate at the tip, right? So when you have a sharp point, let's assume our metal object look like this, and I apply a bunch of positive charges. My claim is a lot of positive charges would accumulate here. Other places it will be somewhat more or less evenly spread out, a function of the radius of curvature. So instead of making it into a complex three-dimensional figure, let me make it into a simple one-dimensional object. Right? So let me delete off the bottom. Let me look at just this curve alone. Right? So we have voltage in some kind of length here. So wherever the charges are going to be there, let's assume, so this whole object, right, since it's a metal object, every single point would have to be the same potential, right? That would be a requirement for us. But the problem is because of the sharp structure we have, there's going to be a very large amount of, so this is going to be the same potential as this is going to be the same potential as this is going to be the same potential. Given this curve, how do I get the electric field? So electric field is basically just dV by dl. In this case, V I'm representing in the y-axis, L I'm representing in the x-axis. So dV by dl is just same as saying dy by dx. Right? If I differentiate this curve that I've drawn here, I would basically get the electric field at every single point. So if I differentiate this, wherever there is a discontinuity of some sort, that is where the electric field is going to be maximum. This is where E is going to be the maximum. Just because of the relationship that it's just dy by dx, and this is where the sharp corner points are, and this is all equipotential lines, right? And wherever the sharp corner points are, that's where the voltage suddenly changes rapidly, going from one voltage level to the other voltage level. So at those points, you would end up with extremely large electric field, And what would large electric field do? Make the charges crowd towards those points, right? So around the tips, you would have extremely large amount of charges that crowd, which in turn would then contribute to more electric field, which would in turn contribute to large amount of charge. It's more of a chicken and egg problem. You never know what caused what, but at the end of the day, you end up with a large electric field and crowding of charges. So that was the structure that Andrew Gordon had created, where these tips of these pinwheels accumulate a whole bunch of charge. And if the charge gets large enough, it can start to discharge the air around it. So air is primarily just nitrogen and oxygen. And oxygen is a nice symmetric distribution of its electron distribution function. But in the presence of high charge, the electrons would crowd to one side, the valence electron at least, and then the rest of the orbital proton and the orbital electrons would all crowd to one side, right? It would start to get distorted. And if this is large enough, it can rip out those electrons that are there in the valence band. So those two electrons come out, we end up with 2 O2 minus and 2 electrons hanging around. Same thing happens with nitrogen. Nitrogen being far more inert, it's a little bit difficult to break it down, but oxygen kind of readily breaks down. So if the electric field is large enough and the point at which it breaks down is 3 kV per millimeter, or about 3 million volts, that's a huge amount of potential difference for the given distance. If it's large enough, then the air itself will start to break down. That's what you see as sparking or arcing whenever you cover yourself with your bed sheet in the middle of the winter. When it's extremely dry, you see these sparks going on. You're basically creating this arcing by ionizing oxygen. And if it happens at large enough quantity, which of course no human can produce, you can create, so this free floating electron would then have chance to pair with other 2 more oxygens and create ozone, which is extremely toxic, right? So when we have, how many of you have seen the switchgear opens in power system, right? You see this whole bunch of arcing that goes on. So that's one of the main potent producer of ozone in lower atmosphere, right? Higher atmosphere, it's due to radiation, but lower atmosphere comes from one of those things. So this is a very, so this basically gets ionized, you end up with O2 minus 2 electrons, sorry, O2 plus 2 electrons. And what happens is these 2 electrons get attracted to this positive charge and gets cleared out, leaving behind positive ion alone. So we have positive charge here, these two start to repel each other, and then this whole mechanism starts to rotate. Right? So this was a very primitive motor, just as a demonstration. But a lot of textbooks typically attribute this invention, the first electrostatic motor. So this is called an electrostatic motor. What we saw there was an electromagnetic motor. So a lot of textbooks, a lot of talks, almost everybody attributes this invention to Benjamin Franklin, the $100 bill guy. And the reason being, Benjamin Franklin introduced this thing called Franklin bells. So have anybody done this experiment in high school, Franklin bells, Brazilian apparatus? Okay. So it's a very simple structure. You have some kind of house or a chimney, something, and then there is a bell attached to this, a metallic bell. And then there's another metallic bell which is attached to the ground. And then in between, there is a metallic shell that's left floating so that it can move to either side of these bell and make contact. On a nice sunny day, the earth typically has negative charge, and the air surrounding it typically ends up building up a positive charge. So the earth is typically negative charge, and the air surrounding it typically a whole bunch of positive charge. And somewhat surprisingly, this is about 100 volts for every meter you go up. Right? And a meter is not too large. I'm pretty short, so a meter is about, I think, a little less than my shoulder height. If I were to stand here, right, and the air just in front of me is about 100 volts in potential. Why am I not getting electrocuted? Yep.
To get electrocuted, there has to be current.
Okay. So the charge does not have enough energy to kind of create any form of impact. So once I stand on the ground, the atmosphere is far worse a conductor of electricity compared to me, right? As a human body is far more better conductor of electricity. The minute I stand on this ground, my potential has gone to zero. And the air around me is around, you have the 100 volts potential around it, and then 200, so on and so forth. Right? And the air is a very poor conductor of electricity, so there is not significant amount of current flowing. And even if the air was a very good conductor of electricity, the voltage is large, but the charge is very small. Right? So if you have a capacitor, half CV squared is its energy. I could put 1,000,000 volts on this capacitor. If the capacitance is very close to zero, then the energy in the system is very close to zero. Right? So that's exactly what's happening in the atmosphere. There's a lot of confusion when people first see this 100 volts and stuff, and they'll be like, oh, Tesla created free energy long time back. Excel Energy doesn't want you to see all of those conspiracy theories. Basically, just misunderstanding of what voltages was what energy is. So there's a lot of potential, but there is not that much energy, right? But if you look at the whole scale of the Earth, surface of the Earth, it becomes a very large capacitor at that point. That's what you see in the energy in the lightning. Right? All of this charge, when it accumulates over a small location, and the energy is extremely large, you see the power of the lightning in all of those. Right? It's not that somebody is trying to prevent you from extracting this energy. It's just going to be useless. You could construct a full panel the size of Minnesota, and you might be able to make it same as what a coal power plant in Minnesota would be able to do. Right? So it's not going to help you in any way. Okay, so on a very sunny day, you have this kind of potential. But what happens when you have thunderclouds accumulate? We have thunderclouds above approaching. For whatever reason, not yet still understood. People have been studying it for hundreds of years. And we all know the story of Benjamin Franklin asking some poor kid to fly a kite into the lightning. I don't know how much true it is. I haven't looked it up, but so from back then, or even before that, people have been trying to tame lightning, trying to study it. But we still do not know what causes thundercloud for the most part. There are complicated structure where these structures are inverted, or there may be central portions where it's positive, side portions with negative. But for the most part, it's typically thunderclouds have negative charge on the bottom, positive charge on the top. And one possible explanation is that when H2O rises up, due to significant amount of friction, OH ion, which is being heavier, settles down, H plus ion goes up, being a little bit lighter. But there are theories based on radiation effects and stuff like that, but we still do not know. But we do know this is definitely the structure of charge distribution in a thundercloud, because scientists have flown, brave scientists have flown flights to it, and then measured what the potential would look like at every single point. So we do know that for a fact, though. We just don't know how it's created. So if this is negative charge, what would happen then? The ground beneath it, in that localized area alone, would accumulate a net positive charge. Outside of that localized thundercloud, it would still be effectively negative. Right? Because of capacitive effect, if the top plate is negative, the bottom plate ends up being positive. So this bell that is located on the chimney, since it's insulated by the wood of the house, it's not connected to the ground. This also ends up accumulating the negative charge from the thundercloud on the top. It leaks onto this bell, and then this positive charge ends up accumulating onto this bell, because this is all solid copper. So they would have to be equipotential, no other way. So once this happens, we have a metal shell in between. Think of it like a Coke opening tab or something like that. Right? So if there's positive charge here, negative charges would get attracted to the side, leaving behind positive ions of the metal, which would end up effectively having a positive charge on the side. Due to whatever reason, due to some asymmetry, it can get attracted to this side or this side to start off with. Let's assume it gets attracted to this side. Right? It makes contact with this bell. You can hear a cling. But the minute it makes contact, all the negative charges rushes and gets neutralized by the ground. So this whole bell becomes a net positive charge. What would then happen? It would get repelled by this bell that cleared the charge in the first place, but at the same time get attracted by this bell, which has a net negative charge. And then it will come to this side. What will then happen? The negative charges from here would flow in and neutralize the positive charge, giving it a net negative charge now. So it will be repelled by this, attracted by this, going back and forth, basically warning you of an approaching thundercloud even before it starts to rain. So Benjamin Franklin, one thing he's famous for many things, but one thing he's famous for is not staying in the US. for most of his life, he ended up staying outside. And we all know where he was in the later part. He was basically in France when the Treaty of Paris was signed and when the Civil War, Revolutionary War was happening. But much before that, in 1920 and then middle of 1950 to 70, he was based in England. He was basically a representative for Pennsylvania and other New England states. And when he was based in England, he came upon this device, this exact same device that was created by the Scottish monk called Andrew Gordon. Right? And then when he came to US, he kind of made it popular in the US and the name stuck. It became eponymous with Franklin, called Franklin Bells. And then rest is history, everybody forgets about Andrew Gordon. So going forward, we were going to refer to as Gordon Bells and not Franklin Bells. Right, we have, I think I'm done. We have a little more topics to cover, but we will do that on 5, right? Thank you.